The Milky Way is surrounded by galaxies so small and so faint that, for a long time, they almost escape discovery entirely. These ultra-faint companions carry some of the oldest stars in the universe, almost no gas, and far more hidden mass than visible light suggests. They are fragile, ancient, and nearly invisible, yet they may hold some of the clearest clues to how galaxies first began. If this kind of quiet cosmic mystery draws interest, please like the video, subscribe to the channel, and stay with this journey into the faintest galaxies orbiting the Milky Way. Far beyond the bright spiral lanes of the Milky Way, beyond the crowded bands of stars that shape the familiar form of the night sky, the galaxy opens into a much larger and quieter domain. This is the halo, the broad outer region that surrounds the visible disk and extends far into space. It is not a sharp shell. It is a sparse and diffuse realm, thinly populated by old stars, star clusters, streams of torn stellar debris, hot gas, and a great deal of unseen mass. In this frontier, distance becomes difficult to feel in ordinary terms. The Milky Way does not end where its bright light seems to fade. Its gravity reaches outward through a vast dark volume, and within that volume some of the smallest known galactic companions continue their long existence. The ultra-faint galaxies orbiting the Milky Way belong to this outer setting. They are dim traces within a region where almost everything is already faint. From inside the galaxy, the Milky Way often appears as a flattened river of light, but that appearance is shaped by position. Seen from far away, it would show a luminous disk and central bulge, while much of its true extent would remain harder to see. The halo does not present the strong visual order of the spiral structure. It is looser, wider, and older in character. Its stars are few compared with those in the disk. Its gas is thinner. Its light is weak enough that a casual glance would miss nearly all of it. Yet this outer domain is scientifically important because it preserves fragile systems that survive far from the dense inner parts of the galaxy. Some of the Milky Way's smallest companions dwell there at distances of tens of thousands to hundreds of thousands of light years from the galactic centre, and a few are known at about 500,000 light years from Earth. Leo 4, one example of an ultra-faint dwarf galaxy in the halo, lies about 500,000 light years from Earth and contains only several thousand stars. In a larger galaxy, that number would barely register, but here it is enough to define a whole stellar system. The outer halo feels empty because ordinary matter there is spread so thinly. The dense clouds that build new stars in galactic disks are largely absent. The warm shine of abundant starlight also disappears. Between one system and another lies a great amount of darkness, not as an active presence, but as the natural condition of a region with little luminous material. In this setting, even a galaxy can seem almost unreal. An ultra-faint galaxy is still a galaxy, meaning a bound stellar system held together within its own gravitational structure. But it gives off so little light that it approaches the limit of what large sky surveys can notice. Against the immensity of the halo, such a system does not announce itself. It exists more as a delicate excess of stars than as a bright object. This outer region also belongs to a larger neighbourhood, the Milky Way and the Andromeda Galaxy, together with many smaller galaxies, form the local group. Around this group, matter is not arranged in a simple, uniform way. Recent simulation work places the local group within a broad, flattened sheet of matter that stretches across tens of millions of light years and includes both ordinary matter and dark matter. That result concerns scales much larger than the Milky Way halo itself. Yet it helps show that even the galaxy's remote surroundings are part of a gravitational landscape rather than an isolated void. The ultra-faint satellites of the Milky Way inhabit only a tiny fraction of that larger environment, but they endure within it as some of the least luminous visible structures linked to a major galaxy. The sense of remoteness in the halo is not created by distance alone. It also comes from low contrast. A bright galaxy can be recognized by shape. A bright nebula can be recognized by glow. An ultra-faint satellite in the halo may show neither at first glance. Its stars are so few and so spread out on the sky that they can blend into the foreground stars of the Milky Way and the background of much more distant galaxies. Some are first recognized not by obvious brightness, but by a small concentration of stars standing slightly closer together than the surrounding field. In other words, the halo frontier is a place where a galaxy can exist in plain view and still remain almost hidden. This is why the outskirts of the Milky Way remain unfinished territory. The known population of satellites has grown as surveys have become deeper and more systematic. Yet astronomers do not assume the census is complete. New modelling work suggests that there could be roughly 80 to 100 additional faint satellite galaxies near the Milky Way beyond current detection limits. Other discoveries, such as Virgo 1, point in the same direction by showing that a satellite can be so faint that it nearly escapes notice in modern sky mapping. These results do not mean that all such hidden companions have already been confirmed. They mean that the outer halo is likely richer than it looks, and that the visible sample may still be only a fraction of the true population. Even among objects that have been detected, the outer halo keeps its ambiguity. Some newly found systems sit so close to the boundary between star cluster and galaxy that classification remains uncertain. Ursa Major 3, also called Unions 1, has been described as a tiny stellar system with only about 60 stars that may represent either an extremely faint galaxy or an unusually small star cluster. That uncertainty does not weaken the importance of the halo frontier. It reveals its character. At these extremes, the familiar categories of astronomy begin to thin out, just as the matter of the halo thins out. So the first impression of the ultra-faint galaxies orbiting the Milky Way is one of setting. They dwell in the galaxy's widest and quietest outskirts, in a region where light is scarce, distances are immense, and the visible edge of the Milky Way gives way to a much larger gravitational domain. The outer halo is not empty, but it is economical with light. It preserves small companions in deep darkness and makes them difficult to separate from the surrounding sky. There, on the faint frontier of a large spiral galaxy, some of the least luminous galactic systems known continue to orbit, almost erased by the very environment that holds them. The ultra-faint galaxies do not gather in a neat ring around the Milky Way. They are scattered through the halo in a loose and incomplete pattern, each one moving within the larger gravitational reach of the galaxy, each one occupying a different part of that wide surrounding space. Some lie relatively closer to the Milky Way, deep inside the halo. Others are found much farther out, near the more remote edges of the galactic environment. Between them stretch enormous intervals of darkness. Their distribution is not dense enough to resemble a swarm of bright companions. Instead, it feels sparse, irregular, and only partly revealed, as though the sky contains more of these small systems than the present map can clearly show. This broad arrangement matters because it shapes how the Milky Way is understood as a galactic host. A large galaxy does not live alone. It sits inside a dark matter halo, an extended mass structure that reaches well beyond its visible stars. and smaller systems can survive inside that volume if their own internal gravity is strong enough to resist disruption for long periods of time. The ultra-faint galaxies belong to this family of companions. They orbit within the same larger structure, yet they do so at very different distances and along very different paths. As a result, the population is spread across the sky rather than concentrated in one easy place. The full halo surrounds the Milky Way in 3 dimensions, but Earth views that halo from inside the Milky Way itself, through a bright and cluttered foreground of stars, dust, and gas. That interior viewpoint makes the outer distribution harder to read. Seen in this way, the problem is not simply that the galaxies are dim, it is also that they are positioned around a giant system whose own light and structure interfere with a clean census. In some directions, the line of sight passes through especially crowded fields of Milky Way stars. In others, dust near the galactic plane absorbs and reddens light, reducing contrast and hiding weak stellar groupings. An ultra-faint galaxy that lies behind a dense foreground can become almost impossible to separate from the much nearer stars of the Milky Way. Another may sit in a clearer direction and become detectable even if it is not intrinsically brighter. The sky therefore does not offer equal conditions in every direction. The distribution that astronomers currently see is shaped partly by nature and partly by the uneven ease of observation. The ultra-faint population also appears spread across a large range of physical distances. A companion that is nearer may cover a broader patch of sky, while a more distant one may shrink into a barely noticeable grouping. Nearness does not always make discovery easy. If a system is too diffuse, its stars can still disappear into the field. Distance also does not automatically hide everything. A distant object can sometimes stand out if its stars are arranged in a slightly more recognizable excess. What matters is the combination of distance, compactness, stellar content, sky position, and foreground contamination. Because these factors vary from one system to another, the visible population does not reveal a simple edge or a clean pattern. It reveals a patchwork. There is another reason the distribution seems incomplete. The search history of the sky is itself uneven. For many years, large digital sky surveys covered some regions more deeply than others, and many of the first ultra-faint galaxies were found within the footprints of those major surveys. This means the growing map of Milky Way satellites reflects where astronomers have looked with sufficient depth as much as it reflects where the satellites truly are. A cluster of discoveries in one region of sky does not necessarily mean that nature has favoured that region. It may also mean that the observations there have been especially sensitive. As deeper surveys extend to other parts of the sky, the apparent pattern changes. New faint systems appear in regions once thought relatively quiet, and the sense of emptiness begins to soften. This incomplete distribution is one reason astronomers remain cautious when they speak about the total number of Milky Way satellites. The known sample is real, but it is not assumed to be the whole population. Modelling studies increasingly suggest that many more tiny companions should exist than have yet been confirmed. Some recent work argues that there may be roughly 80 to 100 additional satellite galaxies around the Milky Way beyond those already recognized. These would not be bright missing objects in an ordinary sense. They would be systems so small and faint that they slip below present limits or blend into more familiar structures on the sky. Their expected existence strengthens the impression that the visible population is only the brighter upper layer of a much larger and dimmer family. The spatial pattern may also carry traces of shared history. Not every small companion necessarily arrives alone. Some may fall into the Milky Way as members of a group, entering together within the gravitational influence of a larger satellite system. This possibility helps explain why some companions can appear associated in broad orbital families rather than fully random placement. The Milky Way is not merely surrounded by isolated points. It is also a system that grows through accretion, the gradual capture of smaller structures over cosmic time. In that process, faint satellites can be brought inward, spread apart, or partially disrupted, yet still preserve hints of where they came from. Even so, the present view remains incomplete enough that astronomers avoid forcing a strict visual order onto the whole population. The result is a sky in which the ultra-faint galaxies are both present and elusive. They orbit a giant host, but they do not trace its shape in any obvious way. They occupy remote parts of the halo, but not only its farthest edges. They are more likely to be found where the observing conditions are favourable, yet they almost certainly exist beyond the regions already searched well. Around the Milky Way, the smallest companions form a hidden geography rather than a finished map. Their positions suggest a real population spread through the halo, but the pattern remains only partly visible because the Milky Way is bright, the halo is vast, and the companions themselves contribute almost no light. In this broad region around a giant galaxy, absence on the map does not necessarily mean absence in space. It often means only that darkness, distance, and foreground clutter still keep much of the population concealed. To find an ultra-faint galaxy, astronomers usually do not begin with the impression of a galaxy at all. There is no glowing spiral, no bright central bulge, no clear cloud of diffuse light standing out against darkness. In most cases, what appears first is only a slight statistical irregularity in the sky, a place where a few stars seem to gather a little more closely than the surrounding field. The search therefore begins not with dramatic images, but with patience, counting, comparison, and careful separation of one stellar population from another. In the outer halo of the Milky Way, this is how one of the faintest classes of galaxies becomes visible. A normal bright galaxy can often be detected through its integrated light, meaning the blended glow of many unresolved stars seen together as a continuous form. Ultra-faint galaxies are different. Their total light is so weak, and their stars are so few, that the combined glow often sinks below the background of the sky. Instead of appearing as a luminous patch, they dissolve into individual points. The practical task is then to search wide survey images for small overdensities of resolved stars. An overdensity is simply a region where more stars appear than expected by chance. This sounds straightforward, but the sky contains countless chance patterns. A few stars near one another may mean nothing. A real ultra-faint galaxy must be extracted from a sea of misleading alignments. Modern sky surveys make this possible because they image enormous areas of sky deeply enough to record very faint stars. Digital catalogues then measure the position, brightness, and colour of each source. Astronomers can sort these sources and ask whether a particular patch of sky contains stars that behave like a coherent population, rather than a random crowd. Colour matters because stars in an old, metal-poor system tend to occupy recognisable sequences in a colour magnitude diagram, which is a plot of stellar brightness against colour. A technical term appears there, but its purpose is simple. It helps show whether a group of stars may share age and chemical history. If several stars in one small region line up in a way expected for an ancient stellar system at one common distance, the region becomes more interesting. This method turns discovery into a layered filter. First comes broad imaging across large parts of the sky. Then software and human inspection search for weak concentrations of stars. After that, Astronomers compare the candidate stars with models of old stellar populations. Foreground stars of the Milky Way must be removed as well as possible, and faint background galaxies that masquerade as stars must also be reduced. Only then does a possible ultra-faint galaxy begin to emerge from the data. It is often less like finding a lamp in darkness, and more like noticing that a handful of grains on a dark surface are arranged with unusual order. Leo 4 offers a clear example of how subtle this process can be. NASA describes it as star-starved and difficult to spot even in Hubble views. It was first noticed in Sloan Digital Sky Survey data because astronomers found a region where stars were huddled more closely together than in neighbouring areas. That phrasing captures the heart of the method. The discovery did not begin with a bright galactic shape. It began with counting stars and recognizing that the count in one place was just high enough and just coherent enough to justify closer attention. Even after such a system is identified, the image can remain visually unimpressive. The few stars of the galaxy may still look lost among unrelated foreground stars and distant background galaxies. Virgo 1 shows the same principle on a wider survey scale. It was discovered with the Hyper Suprime Cam instrument on the Subaru telescope, whose combination of large light-gathering power and wide field of view makes it especially useful for searching huge areas for extremely faint companions. Again, the object did not reveal itself through obvious brilliance. It appeared as a tiny stellar system almost at the threshold of detectability. Its importance came partly from what the detection method implied. If a galaxy that faint could be found only when survey depth and sky coverage improved enough, then many more similarly weak systems might still be waiting below older search limits. This is why discovery images of ultra-faint galaxies can feel unspectacular to an untrained eye. The science lies not in visual drama, but in disciplined pattern recognition. Astronomers ask whether the stars in a suspected patch cluster in position, whether their colours suggest a common, ancient population, whether their brightnesses fit one plausible distance, and whether the grouping is more concentrated than ordinary fluctuations in the field. A candidate may survive some of these tests and fail others. Some objects turn out to be loose star clusters. Some remain ambiguous. A few occupy the narrow and uneasy border between a tiny galaxy and a mere cluster of stars. The challenge increases because the signal is so weak. A galaxy with only dozens or a few thousand stars offers little redundancy. Remove a few likely members and the system can nearly vanish. Include too many unrelated foreground stars and the system can seem larger or richer than it truly is. The search is therefore statistical from beginning to end. It depends on probabilities, selection criteria, and follow-up measurements. Astronomers must always ask whether a candidate is real or whether the eye and the algorithm have been misled by the natural roughness of the sky. In this region of research, better instruments do not merely sharpen what is already obvious. They reveal objects that previously had no firm observational presence at all. A deeper survey sees fainter stars. A wider survey samples more of the halo. More precise measurements of motion and brightness help distinguish members from intruders. With each improvement, the census of Milky Way companions changes. The sky itself has not changed. The threshold of visibility has changed. So the faintest galaxies are found by treating the sky not as a picture to admire, but as a field of measured points to interrogate. Their first appearance is often modest enough to seem uncertain. A very small excess of stars, the right colours, the right brightness pattern, and enough coherence to resist dismissal become the first sign of an entire galaxy. In the outer halo of the Milky Way, this is how almost invisible systems step into scientific view. They're not found because they shine strongly. They're found because careful surveys learn how to notice that, in one tiny patch of sky, the stars are arranged in a way that chance alone is unlikely to produce. An ultra-faint galaxy does not look like the usual idea of a galaxy. It does not display sweeping arms, a bright nucleus, or a dense glowing haze with a clear edge. Its outward form is quieter and far more difficult to grasp. In images, it often appears as little more than a thin scattering of stars spread across a small patch of sky. Even when astronomers already know where it is, the eye can struggle to accept that the pattern belongs to a galaxy at all. The defining visual impression is weakness. The light is so sparse that the system seems to hover on the edge between presence and disappearance. This weakness is described by astronomers through surface brightness, which means how much light is spread across a given area of sky. A galaxy can contain enough total light to be real and measurable, yet still remain hard to see if that light is distributed very thinly. Ultra-faint galaxies belong to this extreme. Their stars are not packed into a bright central glow. Instead, the light is diluted over an area large enough that the whole system becomes nearly indistinguishable from the sky background. This is why such galaxies can be missed even when their total brightness is not zero in any meaningful sense. The problem is not just faintness in the total amount of light. It is the extreme thinness of that light when laid across the sky. A brighter galaxy can announce its presence through shape before any details are known. An ultra-faint galaxy usually cannot do that. At first glance, there may be no obvious continuous body, only resolved stars separated by darkness. The human eye tends to recognize objects by contrast and contour, but these systems offer very little of either. Their outlines are soft, uncertain, and often dependent on statistical analysis rather than direct visual certainty. If the stars belonging to the system are marked and isolated, the galaxy becomes easier to imagine. Without that assistance, it can seem as though nothing coherent is present. The outward appearance is therefore partly physical and partly observational. The galaxy is intrinsically dim, and the visual system that tries to detect it is working at the limit of what it can separate from noise. Most ultra-faint galaxies also lack the rich internal structure that makes larger galaxies visually memorable. There is no bright disk of ongoing star formation, no dark lanes of dust, and no broad colour contrast between crowded young regions and quieter old ones. Their appearance is simple, because their material is simple in outward terms. They present an ancient, stripped-down look, one in which individual stars matter more than blended luminosity. In some well-studied examples, only a few thousand stars, or even fewer, define the visible body. NASA describes Leo 4 as star-starved, and that phrase captures the appearance well. A star-starved galaxy is not empty, but it is visually austere. It offers only a minimal visible trace of a much larger gravitational reality. This sparse appearance also affects apparent shape. Many ultra-faint galaxies are roughly round to mildly elongated when astronomers model their stellar distribution, but the form is rarely crisp. A brighter galaxy can show a boundary where the light falls away in an orderly manner. In an ultra-faint galaxy, the fall-off is so gentle and the stellar counts are so low that the body seems porous. The system looks almost unfinished, as though it were only a loose suggestion of a galaxy rather than a full expression of one. This impression can be misleading. The galaxy is not unfinished in a physical sense. It is only very small, very dim, and seen under observational conditions that make smooth structure hard to recover. Distance adds another layer to this appearance. Because many of these systems lie far into the Milky Way halo, The stars that compose them are already faint before their sparse arrangement is considered. A galaxy nearer to Earth can sometimes yield a broader and clearer distribution of member stars across the sky. One farther away may compress into a tighter patch, but the individual stars then become harder to measure. In both cases, the overall look remains modest. Nearness does not turn the system into a grand visible object. Farness does not erase it completely if enough stars can still be resolved. What remains constant is the low visual density of the starlight. The colour of an ultra-faint galaxy is also understated. Since these systems are dominated by old stars, their light generally leans toward the muted tones expected from ancient stellar populations rather than the blue-white emphasis often associated with vigorous recent star formation. Yet even this description can overstate what the eye sees. In ordinary images, the colours are not dramatic. The system is usually too faint for colour to dominate the impression. Shape and brightness are already so weak that colour becomes a subtle scientific property more than an obvious visual one. The overall look remains one of pale, elderly starlight scattered thinly across darkness. Some of the most intriguing cases show how little is required for a galaxy-like appearance to become uncertain. A tiny stellar system such as Ursa Major 3, with only a very small number of likely stars, begins to push outward appearance toward the boundary of meaning. At that scale, the difference between a small galaxy and a faint star cluster is not something the eye can settle. The outward look alone becomes insufficient. Even so, the visual lesson is important. The smallest galactic companions of the Milky Way do not resemble miniature versions of large galaxies in any dramatic pictorial sense. They resemble slight stellar assemblies whose galactic nature must be inferred from the pattern, scale, and behaviour of their stars. This is why discovery images of ultra-faint galaxies often feel almost empty. The object is present, but presence takes a restrained form. A few stars appear where very few stars should be. Their arrangement hints at a coherent body. Their combined light is real but diluted. Their overall outline is soft. The galaxy does not dominate the frame, it barely inhabits it. Against the rich expectations created by the word galaxy, the actual appearance can feel surprisingly modest, even severe. Yet that modesty is part of the scientific meaning. It shows how small a galaxy can become in visible terms while still remaining a true galactic system. So the outward appearance of an ultra-faint galaxy is defined by restraint. It is a galaxy reduced almost to its minimum visible expression. With light spread so thinly that the system approaches invisibility, its stars are few, its body is loose, its brightness is low, and its shape is more suggested than declared. In the halo of the Milky Way, such a system appears not as a bright island of starlight, but as a delicate stain of ancient stars that only careful attention can hold together as one object. The ultra-faint galaxies do not remain fixed in the halo of the Milky Way. They move through it under gravity, tracing long paths around a much larger host. These paths are not visible in the sky as drawn lines, yet they are real and persistent, shaped by the mass of the Milky Way and by the earlier history of each small companion. In the outer halo, motion is quiet in appearance but powerful in meaning. A satellite galaxy may spend hundreds of millions or billions of years crossing great distances, falling inward, swinging around the deeper part of the Milky Way's gravitational field, and then moving outward again. The orbit is not a simple decorative curve. It is the long-term framework within which the satellite survives, changes, or gradually comes apart. To say that a galaxy orbits the Milky Way means that it remains gravitationally bound to the larger system. It is not drifting freely through unrelated space. The Milky Way's dark matter halo, together with its visible matter, creates a deep gravitational well, and the ultra-faint companions move within that well. Some follow wide orbits that keep them far from the bright inner regions for most of their history. Others travel on more elongated paths that bring them closer in at certain times and send them far back out at others. These motions differ from the nearly circular orbital picture that is often imagined for planets around a star. Satellite galaxies inhabit a much more complex environment. Their paths can be tilted at many angles, stretched into long ellipses, and altered over time by interactions with the Milky Way and with other companions. Because the halo is so large, these orbits unfold across enormous distances. A satellite may lie tens of thousands of light-years from the Milky Way at one stage of its path and much farther away at another. The speed of motion is substantial in physical terms, often hundreds of kilometers per second, but the scale is so great that the movement still feels gradual. Over the span of one human life, the orbit hardly changes in any visible way. Over cosmic time, however, the path becomes a repeating or slowly evolving journey through the halo. This contrast gives the outer Milky Way a calm appearance, even though every member of the system is in motion. Astronomers study these paths by measuring the positions, distances, line-of-sight speeds, and, when possible, the proper motions of the satellites. Proper motion means the tiny drift of an object across the sky as seen from Earth. For distant and faint systems, that drift is extremely small and difficult to measure. But modern data, especially from missions such as Gaia, have made such work increasingly possible for some Milky Way companions. When those measurements are combined, they begin to reveal whether a satellite is moving inward, outward, or around the galaxy in a broader looping path. In this way, the orbit is reconstructed not by direct visual tracing but by careful inference from velocity and position. The form of an orbit matters because it controls the environment a satellite experiences. A galaxy that stays far out in the halo moves through a quieter gravitational setting. A galaxy that plunges inward encounters stronger tidal forces, meaning stronger differences in the Milky Way's pull from one side of the satellite to the other. These differences can stretch the satellite, heat its stellar motions, and slowly remove material from its outer parts. The path itself therefore becomes part of the satellite's history. Two galaxies with similar beginnings may not remain similar if one follows a gentle outer orbit, while the other repeatedly passes through harsher inner regions of the halo. Not all ultra-faint galaxies necessarily arrive around the Milky Way in isolation. Some may enter as part of a small group that once orbited a larger companion system, before the whole collection fell into the Milky Way halo. In that case, related satellites can preserve hints of shared motion or similar orbital planes, though the full pattern is often difficult to determine with certainty. The halo is not static enough to preserve every detail forever. Over long periods, gravitational interactions spread systems apart and alter their trajectories. Even so, the present orbits may still carry memories of how these companions were accreted, meaning how they were gradually added to the Milky Way through cosmic growth. The path of an ultra-faint galaxy is also shaped by the mass distribution of the Milky Way itself. The orbit does not respond only to the visible disk and bulge. It responds mainly to the larger dark matter halo that surrounds them. This means that the satellites move inside a gravitational structure far larger than the bright galaxy alone would suggest. In a sense, The orbit of a tiny companion becomes one of the ways astronomers probe the invisible architecture of the Milky Way. If many satellites are mapped well enough, their motions help constrain how mass is spread through the halo. The movement of the smallest companions therefore has value far beyond the companions themselves. Yet the picture is never perfectly clean. Ultra-faint galaxies are hard to measure precisely because they contain so few stars and contribute so little light. Distances carry uncertainty. Proper motions can remain limited. Membership of individual stars may be ambiguous. As a result, the exact orbital history of a given system is often not fully known. Observations indicate broad classes of behavior, such as bound motion through the halo and the importance of close passages to the Milky Way. But it remains uncertain in many individual cases how many times a satellite has circled the galaxy or how close it has come in the past. This uncertainty does not erase the general truth of orbital motion. It only reminds astronomy that the faintest companions are observed near the edge of precision. What matters most at this regional scale is that the halo is not merely a storage space for dim objects. It is a dynamic environment. Every ultra-faint galaxy within it is moving, and that movement is central to its fate. A quiet outer orbit can allow a fragile system to persist for immense spans of time. A more plunging path can expose it repeatedly to stronger forces and gradual distortion. The distribution of satellites around the Milky Way is therefore not just a map of where they are. It is also the temporary result of where their orbits have carried them. In the halo of the Milky Way, the ultra-faint galaxies travel on long, patient routes through darkness. Their paths are governed by unseen mass, altered by time, and measured only with care. They do not circle like neat ornaments. They move as survivors inside a vast gravitational system, each one tracing a slow arc that reflects both the Milky Way's depth and its own long history of motion. At the outer edge of an ultra-faint galaxy, the sense of fragility becomes strongest. The main body of the system does not end with a hard boundary or a visible wall. Instead, its stellar population thins outward until the last loosely bound stars approach a region where the gravity of the small galaxy is no longer clearly dominant over the pull of the Milky Way. This is the tidal edge, not a sharp line drawn in space, but a transition zone where competing gravitational influences begin to matter more and more. In a large bright galaxy, the outskirts may still contain enough stars and gas to give the impression of continuity. In an ultra-faint galaxy, the outskirts are already so sparse that even a mild external disturbance can become important over long spans of time. The word tidal here refers to a difference in gravitational pull across the satellite. The side of the small galaxy that lies slightly nearer to the Milky Way feels a stronger pull than the far side. In a large, tightly bound system, this effect may remain modest. In a tiny, low-mass, diffuse system, it can gradually reshape the outer regions. The stars nearest the edge are the least securely held. They orbit within the small galaxy, but they do so in a part of the system where the local gravitational grip is weak. If the Milky Way's differential pull becomes comparable to that grip, those stars may be shifted, heated, stretched into a more elongated distribution, or slowly removed altogether. This process is not usually sudden. The tidal edge is a place of long attrition rather than instant destruction. A star at the outskirts of an ultra-faint galaxy does not simply decide in one moment to leave. Instead, repeated passages through the Milky Way's gravitational field, especially during closer approaches to the host galaxy, can inject small changes into the star's motion. Over many orbits, those changes accumulate, the outer structure becomes less regular. The galaxy can grow more elongated. Some stars move onto paths that no longer remain fully bound to the satellite. The result is gradual stripping, a slow loss of the most weakly held material at the edges. Because ultra-faint galaxies contain so few visible stars, even modest stripping can matter. In a larger system, the loss of a small outer fraction might barely change the overall appearance. In an ultra-faint system, the outer population is already limited enough that every star near the boundary contributes noticeably to the visible shape. A few stars pulled away from the outskirts can make the body seem more irregular, more porous, or more stretched. This is one reason the boundaries of these galaxies are often difficult to define with precision. The edge is not only faint, it may also be dynamically active on long timescales, shaped by the continuing influence of the Milky Way. The tidal edge therefore marks a balance point. Inside it, the ultra-faint galaxy still behaves as a coherent system, with stars moving mainly under the gravity of the satellite and the invisible mass that surrounds it. Near and beyond it, that coherence weakens. The Milky Way begins to compete more openly for control of the star's motions. Some stars may still linger near the system after becoming only weakly bound or fully unbound. Others may drift into faint tidal debris, thin stellar extensions that are extremely difficult to detect in systems this dim. Observations of ultra-faint galaxies do not always reveal these extensions clearly, because the signal is so weak, but the physical expectation remains important. A very small satellite in a giant halo lives close to the limit of what can remain intact. The orbit of the satellite strongly influences how harsh this boundary becomes. A galaxy that remains far from the inner Milky Way spends most of its time in a weaker tidal environment, and its edge can survive with less disturbance. A galaxy whose orbit carries it inward experiences stronger gradients in the Milky Way's pull. In those cases, the outer stars are exposed to a more severe test. The tidal edge may move inward, meaning that a larger fraction of the visible body becomes vulnerable. This does not always lead to complete destruction. Some ultra-faint systems appear to survive for billions of years despite this pressure. Yet survival does not mean perfect preservation. It can mean enduring while slowly losing the least protected stars. This tension between survival and erosion gives the boundary region much of its scientific interest. The edge preserves evidence of how the satellite and the Milky Way interact. If the outer stars show a symmetry, elongation, or unusual dispersion, astronomers consider whether tidal influence is responsible. In some cases, the outer structure may suggest that the system is still largely intact. In others, it may hint that disruption is underway. Recent discussion around systems such as Ursa Major 3 or Unions 1 shows how delicate this issue can become. A very small stellar system moving through the Milky Way's halo may be interpreted as a tiny dark matter-dominated galaxy that has managed to resist disruption, or as a system observed near a brief stage before more serious disintegration. The faintness of such objects makes certainty difficult, but the role of tidal stress is impossible to ignore. The tidal edge also explains why outward appearance alone can be deceptive. A stretched or irregular outline does not necessarily mean that the system was born that way. It may reflect the cumulative effect of the Milky Way's gravity working on a fragile boundary over immense periods of time. A sparse system may look unfinished because its outskirts are genuinely unstable. Another may still appear compact because its orbit has spared it from stronger stripping. The visible edge is therefore not just a shape, it is a record of exposure to the surrounding halo. In these outer layers, the ultra-faint galaxy reveals how close it lives to loss. Its stars become fewer, its gravitational hold weaker, and the influence of the Milky Way more direct. There is no dramatic line where galaxy stops and host begins. There is only a fading transition in which the smallest companion struggles to keep its most distant stars. This is the fragile limit of an ultra-faint galaxy, the place where a tiny system meets the deeper gravity of the Milky Way, and where survival becomes a matter of how much of the outer body can remain bound, passage after passage, through the dark halo. The visible body of an ultra-faint galaxy is remarkably small. In a large galaxy, the eye and the instrument encounter abundance. There are vast numbers of stars, broad luminous regions, and enough blended light to create a clear impression of a stellar city. In an ultra-faint galaxy, the visible body is reduced to something much more delicate. It may contain only a few thousand stars, and in the most extreme cases perhaps far fewer, yet this smallness does not make it unreal. The visible body is slight, but it is still the outward expression of a genuine galactic system. What makes this body unusual is not only the low number of stars, but the way those stars are arranged. They do not usually crowd into a brilliant central knot. They are spread thinly through a modest volume of space, forming a loose stellar assembly whose coherence becomes apparent only when the member stars are considered together. This assembly is the visible part of the galaxy, the portion that astronomers can trace directly through starlight. Even when the system is hard to see in an ordinary image, its stars still occupy a shared structure. They lie at nearly the same distance, gather in a limited region, and create a body that is sparse but not random. NASA describes Leo 4 as containing several thousand stars, and that is a useful scale to hold in mind. Several thousand stars sound numerous in ordinary life, but in galactic terms the number is extraordinarily small. A rich star cluster can also contain large numbers of stars, and a major galaxy contains them in overwhelming profusion. The visible body of an ultra-faint galaxy therefore lives near the lower boundary of what can still be counted as a galaxy in observable terms. It is not a miniature spiral. It is not a bright reduced copy of a larger system. It is a very small stellar body with just enough luminous matter to remain legible as a separate system. This sparseness affects every visual property of the body. The stellar density is low. The stars are separated by darkness. The center may contain a somewhat higher concentration than the outskirts, but even there the system seldom looks crowded in the way a globular cluster can look crowded. Instead, the visible body gives an impression of restraint. The stars occupy the same general home, yet they do so with wide spacing and weak overall light. In some objects, the body can feel almost skeletal, as though only the minimal visible framework of a galaxy has been left in place. The size of the visible body is also modest in physical extent. It is often measured in a few hundred light-year across, sometimes more, sometimes less, depending on how the stellar distribution is defined. This is large enough that the body is not just a tight knot of stars. At the same time, it is small compared with the more expansive stellar domains of brighter dwarf galaxies. The result is a body that is both extended and meagre. It occupies real space, but fills that space with very little luminous material. That combination helps explain why an ultra-faint galaxy can be hard to detect. The stars are not packed tightly enough to create a strong central beacon, yet they are spread out enough to define a genuine little stellar system. Within this sparse body, the stars do not all contribute equally to visibility. A few brighter giants can make the first impression easier to notice, while many dimmer stars carry much of the actual population but contribute less obvious light. The visible body is therefore shaped not only by how many stars are present, but by how that small population is divided among brighter and fainter members. A system with the same total number of stars can appear more or less obvious, depending on how many of them are bright enough to stand out in a survey. This is one reason why the visible body of an ultra-faint galaxy is not simply a head count. It is a thin stellar community whose detectability depends on how its members distribute their light. The body also tends to be simple in form. There is usually a central region where the stellar density is highest, then a gradual thinning outward. The decline is not abrupt. The stars fade into lower and lower surface density until the galaxy becomes hard to separate from the surrounding field. Because so few stars define the system, the body can appear irregular at first glance. Small number statistics matter strongly here. In a giant galaxy, irregularities are softened by the huge population of stars. In an ultra-faint galaxy, each visible star carries more visual weight. A slight asymmetry in the distribution can therefore seem more important, even when the overall body remains broadly coherent. This helps explain why a very small visible body can still belong to a real galaxy, rather than to a chance grouping. The stars are not merely close in projection on the sky. They form a structured stellar body with a measurable center, a measurable extent, and a distribution that persists under analysis. Even when the population is tiny, the system behaves as more than a casual gathering. This is especially important near the lower limit, where tiny stellar systems challenge ordinary categories. A visible body made of only dozens or a few hundred likely stars may look almost too slight to deserve the word galaxy. Yet the decision does not rest on visual richness. It rests on whether those stars truly belong to a common bound system of galactic scale. In this sense, the visible body of an ultra-faint galaxy teaches an important lesson about scale. A galaxy does not need overwhelming light to be a galaxy. It does not need ornate structure or a crowded stellar interior. It only needs a real stellar body that exists as one system rather than as an accidental pattern. The ultra-faint galaxies show how far that principle can be pushed. Their bodies are so poor in stars that they nearly vanish into the sky, yet enough remains to preserve their identity. So the main stellar body of an ultra-faint galaxy is small, diffuse, and quietly coherent. It contains very few stars by galactic standards, spreads them across a modest but real extent, and forms a visible structure that can be recognized only with care. In the Milky Way halo, these bodies do not impress by abundance. They endure by barely enough light, just enough stars, and just enough structure to show that even a very thin stellar assembly can still be a true galaxy. The stars that make up an ultra-faint galaxy are usually very old. This is one of the clearest and most important features of these systems. In the Milky Way halo, their faint visible bodies are not built from a mixture of many recent stellar generations. They are dominated instead by populations that formed early, long ago in the ever since. When astronomers study these galaxies closely, they often find that the starlight comes mostly from ancient stars whose ages reach back more than 12 billion years. In some well-known cases, the dominant populations appear to be more than 13 billion years old. These are stars that belong to the deep past. Their light arrives now, but their origins lie near the beginning of galactic history. This great age changes the meaning of the galaxy's faintness. An ultra-faint galaxy is not dim because it is young and unfinished in the way a forming system might be young and unfinished. It is dim because it is ancient, small, and poor in stars. The visible population is like a preserved remnant. It no longer shows the lively contrast that comes from repeated strong episodes of star formation across cosmic time. Instead, It presents a population whose main growth happened early and whose later history remained quiet. The stars that shine today in such a galaxy are largely old survivors rather than members of a continually renewed stellar society. Ancient stellar populations have recognizable characteristics. They tend to contain many long-lived, low-mass stars, which burn their fuel slowly and can survive for immense spans of time. They also contain a smaller number of evolved stars that have moved into later stages of stellar life, becoming more luminous and helping astronomers identify the age of the system. A galaxy dominated by old stars therefore does not need to be bright to tell its story. Even a sparse population can reveal its antiquity if the stars occupy the right positions in the colour and brightness patterns used in stellar astronomy. By comparing those patterns with well-understood models and with old star clusters, astronomers can infer that the system formed most of its stars in the distant past. This old age gives ultra-faint galaxies a special place among galactic systems. They preserve not the present vitality of star formation, but the fossil light of an early epoch. A fossil in this context does not mean that the galaxy is dead in an absolute sense. The stars are still physically alive, still shining, still following their own long internal evolution. The word instead means that the overall stellar population preserves evidence of conditions from a much earlier cosmic time. The galaxy does not frequently refresh itself with new generations of stars. It carries forward an old record with relatively little alteration. In that sense, the stellar population functions like a historical archive written in starlight. The age structure of these systems is often surprisingly simple. In many larger galaxies, one can speak of young stars, intermediate age stars, and old stars mixed in different proportions across different regions. In ultra-faint galaxies, the dominant impression is much narrower. The population is overwhelmingly old, and any later star formation appears limited or absent. This simplicity matters because it means the visible body is not only small, it is also temporally concentrated. Much of the stellar mass belongs to an early burst or early series of bursts rather than to a long continuing history. The galaxy is therefore easier to read in one sense and harder to explain in another. It is easier to read because the dominant age signal is clear. It is harder to explain because such early formation and long silence demand a reason in the broader history of the universe. From the point of view of appearance, ancient populations also contribute to the subdued look of these galaxies. Young stars can be bright, blue, and visually assertive. Old populations tend to produce softer, quieter light, dominated by stars that have aged far beyond the brilliant first stages of stellar life. This does not mean every visible star in an ultra-faint galaxy is dim in the same way. A few evolved stars can still stand out, but the collective impression remains that of old age. The galaxy's light feels mature, restrained, and long settled. Its visible body lacks the signs of recent stellar youth. This ancient character is not an incidental feature of one or two examples. It appears again and again in studies of ultra-faint Milky Way companions. The recurrence of the pattern suggests that these galaxies are not simply ordinary dwarf galaxies reduced in size. They are systems that preserve a very early mode of galactic existence. Their stars form near the beginning, and the resulting population remains in place as the surrounding universe changes around them. While larger galaxies continue to grow, merge, and renew their stellar contents in more complicated ways, the ultra-faint galaxies often seem to remain as much older witnesses, carrying early stellar populations into the present day. The age of the stars also changes how the galaxies are valued scientifically. Because the populations are so old, the systems become windows into the early stages of galaxy formation. Their stars do not only show what the galaxies are now, they also preserve clues about what small galaxies were like when the universe was young. The visible body of an ultra-faint galaxy is therefore not merely sparse. It is ancient in a way that gives even a very small number of stars unusual importance. Each old star belongs to a population that has endured almost the full length of cosmic history. So the stellar populations of ultra-faint galaxies are defined above all by age. These are not systems full of recent activity. They are old assemblies whose stars formed early and remained. Their light is the light of long survival. In the outer halo of the Milky Way, their visible bodies seem faint, partly because they contain so few stars, but also because those stars belong mostly to the distant past. The galaxy that appears almost invisible in the present is, in many cases, a preserved survivor from near the beginning, carrying ancient starlight quietly through the darkness. In astronomy, the word metals has a broader meaning than it has in ordinary life. It does not refer only to substances such as iron, copper, or gold. It means all chemical elements heavier than hydrogen and helium, carbon, oxygen, magnesium, calcium, iron, and many others all fall into this category. This definition matters because the stars in ultra-faint galaxies contain very small amounts of these heavier elements. Their chemistry is poor in metals, and that poverty is one of the clearest signs that these galaxies preserve a very early and only lightly enriched record of cosmic history. The first matter in the universe consists almost entirely of hydrogen and helium, with only tiny traces of lithium. Heavier elements are made later inside stars and in explosive stellar deaths. Each generation of stars can enrich the gas around it with more metals, and later generations can then form from that enriched material. In a galaxy with a long and active history of star formation, this process gradually raises the metal content of the stars. In an ultra-faint galaxy, the process appears to have remained limited. The stars that survive today often formed from gas that had experienced very little chemical enrichment. Their atmospheres still preserve that record. This is why astronomers describe ultra-faint dwarf galaxies as among the most metal-poor stellar systems known. Their stars do not only look old, their chemistry also points to an early time when the universe had not yet been enriched by many generations of stellar life. A metal-poor star is not deficient in every sense. It still contains mostly hydrogen and helium, like other stars. What differs is the proportion of heavier elements mixed into that material. In ultra-faint galaxies, that proportion is often extremely small. Some stars in these systems belong among the most iron-poor stars ever found in the neighborhood of the Milky Way. The chemical restraint of these galaxies gives their light a special historical value. A bright star in a metal-rich environment carries the record of many earlier stellar generations. A star in an ultra-faint galaxy may carry the imprint of only a very small amount of prior enrichment. In that sense, the chemistry of the system feels close to the beginning, not completely pristine, because truly metal-free stars have not been found in these galaxies, but still close enough that the difference between one element and another can tell astronomers about the earlier supernovae that seeded the gas. The stars are therefore not only old witnesses, they are chemically simple witnesses. This simplicity, however, is not perfect uniformity. Even a very small galaxy can contain stars with somewhat different metal abundances. That spread matters. A spread means that the galaxy is not just a single burst frozen into one exact chemical state. It has undergone at least some degree of self-enrichment, which means that one generation of stars contributes metals that later stars inherit in slightly greater amounts. In larger galaxies, the chemical range can become broad and layered across space and time. In ultra-faint galaxies, the spread is usually much narrower, yet it is often still present. That is enough to show that even the smallest galactic systems can sustain a limited internal chemical history. The low metal content also helps separate these galaxies from a simple collection of unrelated stars. Chemistry can reveal kinship. If stars in one tiny system share a similarly ancient, metal-poor character, and if their abundances show a pattern consistent with a small common history, the case strengthens that they belong to a real galaxy. In some borderline systems, the presence of a genuine metallicity spread has been treated as an important clue that the object is more galaxy-like than cluster-like. A star cluster can be chemically simpler in certain ways, while a galaxy, even a very small one, can preserve evidence that its gas was enriched over time by more than one event. The chemical record therefore contributes to classification, not only to historical interpretation. The specific element patterns in ultra-faint galaxies can be subtle and sometimes surprising. Many stars show enhancement in elements associated with the deaths of massive stars, while neutron capture elements, which are made through processes that build very heavy nuclei, can be extremely scarce in some systems. Other ultra-faint galaxies contain evidence for rare enrichment events that left unusually strong heavy element signatures in a small stellar population. Because the number of stars available for study is so small, one unusual star can influence how the whole system is interpreted. Even so, the broad impression remains steady. These galaxies are chemically primitive by comparison with larger and more chemically evolved galaxies. That primitive quality does not mean chemically empty. It means lightly processed. The stars still contain the elements needed to reveal an early enrichment history, but not in large quantities. Their atmospheres suggest that the gas from which they formed is touched by only a modest number of prior stellar deaths. The system has not been enriched over and over across a long, vigorous history. Instead, it seems to have passed through only a small amount of chemical evolution before much of its visible history fell quiet. The result is a stellar population whose chemistry remains close to the low metallicity conditions of the young universe. This makes ultra-faint galaxies valuable laboratories for near-field cosmology, the study of the early universe through nearby surviving systems. A large distant galaxy can show the young cosmos only indirectly. An ultra-faint galaxy close to the Milky Way can preserve ancient, metal-poor stars that formed early and still exist within reach of detailed spectroscopy. Spectroscopy is the splitting of starlight into its component wavelengths so that chemical elements can be identified. Through this method, astronomers read the abundance of iron, carbon, calcium, magnesium, and other elements in individual stars. The resulting patterns help reconstruct how little enrichment occurred and how small galaxies begin building a chemical record. So the chemistry of an ultra-faint galaxy is defined above all by scarcity, metals, meaning all elements heavier than helium are present, but only in very small amounts. The stars are poor in heavy elements because they preserve a history with little chemical processing and only limited self-enrichment. Their abundances are not random. They form a thin but meaningful record of ancient stellar activity. In the Milky Way halo, these dim galaxies carry some of the simplest chemical archives known old stars, very low metal content, and just enough internal variation to show that even the smallest galaxies leave behind a real history, written in elements as well as in light. An ultra-faint galaxy contains stars. but it usually contains very little of the cold gas needed to make many new ones. This absence is one of its defining conditions. In larger galaxies, cold gas forms clouds. Clouds develop dense cores, and dense cores collapse to make new stars. That chain gives a galaxy renewal. It allows fresh stellar generations to appear long after the first ones are gone. In an ultra-faint galaxy, the chain is usually broken. The visible body remains, but the raw material for continuing star formation is mostly missing. What survives is a quiet stellar system, with little present capacity to build a younger population. Cold gas matters because stars do not form directly from diffuse, warm material spread thinly through space. They form when gas cools enough to gather, contract, and become dense under gravity. In a small, faint galaxy, this requirement becomes difficult to meet. The system has very little ordinary matter to begin with. Its visible body is sparse, and the amount of gas associated with it is often extremely low or undetectable. Even if gas once existed in greater quantity, the galaxy's weak gravitational hold on normal matter makes retention difficult. A small galaxy can keep stars for long periods if they are already formed and dynamically bound. But gas behaves differently. Gas can be heated, stirred, displaced, or removed more easily than stars. This difference lies at the heart of the silence seen in many ultra-faint systems. When astronomers observe the Milky Way's ultra-faint companions, they usually do not find strong evidence for ongoing star formation. There are no bright nurseries of newborn stars, no glowing emission regions, and no substantial reservoirs of cold neutral gas comparable to those seen in more actively star-forming dwarf galaxies. The systems appear old not only because their stars are ancient, but because the process of renewal has largely ceased. Their light is dominated by survivors from earlier times. Little or no younger generation interrupts that ancient pattern. One reason for this is shallow gravity. The visible stellar body of an ultra-faint galaxy is small, and although the system may sit within a much more massive dark matter halo, the practical retention of gas remains fragile. Gas absorbs energy from its environment. It can be heated by ultraviolet radiation, by shock waves, and by the energy released when massive stars live fast and die. Once heated, gas becomes more extended and easier to push outward. In a tiny galaxy, the escape threshold is low enough that heated gas may not settle back efficiently. Instead, it can expand beyond the region where cooling and collapse would easily resume. The result is not necessarily a dramatic single expulsion. It can be a gradual failure to hold on to star-forming material. Early stellar feedback likely contributes to this outcome. Feedback means the energy and momentum that stars return to their surroundings through radiation, stellar winds, and supernova explosions. In a large galaxy, feedback can disturb gas without permanently ending star formation everywhere. In an ultra-faint galaxy, the balance is more delicate. A small number of massive stars in the early history of the system may inject enough energy to heat and disperse much of the available gas. Because the galaxy is so small, even limited feedback can have lasting consequences. The gas does not need to be blown far in absolute terms. It only needs to be lifted out of the dense central conditions required for further star formation. Once dispersed, it may cool too slowly or remain too vulnerable to external stripping to gather again. The larger environment of the Milky Way also matters. Ultra-faint galaxies live inside the halo of a giant host, not in isolation. As they move through that halo, they can encounter the hot diffuse gas that surrounds the Milky Way. This environment is thin, but over long times it can still matter to very small companions. A satellite moving through an external gaseous medium can lose its own gas through ram pressure, a process in which motion through surrounding material exerts a stripping force. In a larger galaxy, this effect may remove only the outer layers. In an ultra-faint galaxy, where the gas reservoir is already weak, it can be much more consequential. The host galaxy's tides can also disturb the small companion, making gas retention even harder. The visible stars may survive while the gas becomes increasingly difficult to keep. Another problem is density. Even when some gas remains, it may simply be too diffuse to form stars efficiently. Star formation requires not only gas, but gas concentrated enough to collapse. A faint dwarf system with low mass and limited internal pressure support may fail to gather that concentration after early losses. The gas can remain present in trace amounts without reaching the threshold needed for renewed star birth. In that state, the galaxy is not completely empty of ordinary matter, but it is inert in the specific sense that its remaining material no longer organizes itself into new stellar nurseries. This near absence of cold gas helps explain the stark age profile of ultra-faint galaxies. If no substantial gas reservoir survives into later cosmic time, then later generations of stars do not appear in significant numbers. The existing population simply grows older together. The galaxy becomes a place where time passes through stellar evolution rather than through fresh creation. Brighter stars age and disappear. Longer-lived stars continue. The overall population shifts deeper into old age, but the system does not replenish itself. Its visible body becomes a long-lived remnant rather than an active site of ongoing formation. The lack of gas also changes the way the galaxy appears and behaves. Without cold gas, there is no significant internal medium to absorb, cool, and recycle enriched material into later stars. Chemical evolution becomes limited. Structural renewal becomes limited. The galaxy's history settles into a quieter state, in which gravitational survival matters more than the internal growth. A larger star-forming galaxy can change itself from within. An ultra-faint galaxy with little gas changes mainly through passive aging and through the external influence of the Milky Way. This does not mean every ultra-faint galaxy loses its gas in exactly the same way or at exactly the same time. Some may have been shaped more strongly by internal feedback. Others may have suffered more from stripping in the Milky Way halo. Observations indicate the common result clearly, while the precise path for each system can remain uncertain. What is consistent is the outcome. These galaxies show very little cold gas and little sign of recent star formation. Their visible stars are mostly old because the conditions for making younger ones have largely vanished. So the silence of an ultra-faint galaxy is not only visual, it is material. The system lacks the cool, dense gas that allows a galaxy to renew itself. Weak gas retention, early heating, environmental stripping, and low density all work in the same direction. The result is a stellar body that endures without much fresh growth. In the halo of the Milky Way, these tiny galaxies continue to exist, but they do so with little fuel for new beginnings, and with almost no ongoing renewal of the ancient light they already contain. The visible stars of an ultra-faint galaxy tell only a small part of the story. They define the body that can be seen, but they do not account for most of the system's mass. This is one of the central reasons these galaxies matter so much in modern astronomy. Their light is meagre, their stars are few, and their gas is scarce. Yet the systems behave as though they are held together by something far more substantial than their visible contents alone. That unseen component is dark matter, the name given to matter that does not emit, absorb, or reflect light in an ordinary detectable way, but whose gravity still shapes how galaxies form and move. In ultra-faint galaxies orbiting the Milky Way, dark matter is widely understood to dominate the mass budget. This dominance becomes apparent because the stars in these systems are too few and too faint to provide enough gravity on their own. If an ultra-faint galaxy consisted only of its visible stars and whatever small amount of ordinary matter remains, the system would be extremely fragile. Its stars would not be expected to stay bound in the way they do over long periods. The visible body is simply too poor in luminous matter. Yet many of these galaxies persist as recognizable stellar systems within the Milky Way halo. Their survival, despite their low luminosity and their exposure to the gravity of a much larger host, strongly suggests that the stars are embedded inside a more massive invisible structure. This invisible structure is usually described as a dark matter halo. A halo in this sense is not a bright ring or shell. It is an extended distribution of unseen mass surrounding the galaxy. The stars occupy only the inner visible part of the system, while the dominant gravitational framework reaches beyond them. In an ultra-faint galaxy, this relationship is especially striking because the contrast between visible matter and total inferred mass is so strong. A larger bright galaxy also contains dark matter, but its abundant stars and gas can partly mask that fact in the central regions. In an ultra-faint galaxy, the visible material is so limited that the unseen mass stands out more sharply by implication. One way to think about this is to compare light and weight. The light of an ultra-faint galaxy is minimal. It may be produced by only a few thousand stars or even fewer. If light were a reliable guide to total matter in such a system, the galaxy would be one of the least massive structures of its kind. But observations indicate that the gravitational influence associated with the system is much larger than the starlight alone would imply. The galaxy is therefore not just faint. It is faint while still being gravitationally heavier than its visible contents can explain. This is why astronomers often describe ultra-faint dwarfs as some of the most dark matter-dominated galaxies known. The importance of dark matter dominance is not only that it increases the total mass, it also changes what kind of object the galaxy can be. A mere loose grouping of stars without substantial unseen mass would behave differently. It would be more vulnerable to disruption, less able to retain a coherent structure, and less convincing as a genuine galaxy rather than a transient or marginal system. Dark matter gives depth to the gravitational well of the galaxy, meaning that the stars move within a stronger binding environment than luminous matter alone could create. This helps explain why even a tiny visible population can remain part of a real galactic system, instead of dispersing quickly into the background of the Milky Way halo. This unseen dominance is also part of what separates ultra-faint galaxies from ordinary star clusters. A star cluster can contain many stars packed into a small region, but it's not usually thought to reside in its own substantial dark matter halo. An ultra-faint galaxy, by contrast, is understood as a stellar system whose visible component lives inside a much larger invisible mass structure. The stars are the traceable part, but not the main source of gravitational authority. This difference matters greatly when astronomers confront borderline objects. If a tiny stellar system appears to require much more mass than its stars provide, that result supports a galactic interpretation rather than a simple cluster interpretation, though in individual cases the evidence can remain difficult to secure. Dark matter dominance also helps explain why these galaxies are so interesting for cosmology. In many astrophysical settings, ordinary matter complicates the picture. Gas cools, collapses, forms stars, and responds to energy in complex ways. In ultra-faint galaxies, the visible component is so reduced that the systems come closer to showing the underlying role of dark matter in a relatively pure form. They are small laboratories in which the invisible framework appears with unusual clarity. The stars do not overwhelm the system. They act more like sparse traces of a deeper structure. At the same time, this does not mean that every detail is settled beyond doubt. The general view that ultra-faint dwarf galaxies are dominated by dark matter is well established. But the exact amount and inner distribution of that dark matter can remain uncertain. These galaxies are faint enough that the evidence must often be extracted from a limited number of member stars, and small samples always leave room for caution. Some rare galaxies in other contexts have raised debate by appearing to contain unusually little dark matter, but those cases do not overturn the broader pattern seen in the Milky Way's ultra-faint companions. For the class as a whole, the prevailing interpretation remains that dark matter provides most of the mass. This prevailing picture also fits naturally with the earlier features of these systems. Their old stars, their low metal content, and their lack of gas all point to small ancient galaxies that formed early and remained limited in visible growth. Dark matter dominance adds the structural explanation. It says that beneath the thin visible body lies a much more substantial invisible foundation. The stars are ancient, but they are not unsupported. They orbit and endure inside a halo of unseen matter that outweighs them by a large margin. So the central fact of this inner region is simple in concept, even if difficult to measure in detail. The stars that can be seen are not the main substance of the galaxy. The main substance is invisible. Ultra-faint galaxies shine very little, yet their gravity implies much more mass than their light can supply. In the halo of the Milky Way, these tiny systems appear as delicate stellar remnants, but their true structure is deeper and darker than their faint light suggests. They are among the clearest known examples of galaxies in which the visible part is only a thin luminous trace of a far more dominant unseen mass. Inside an ultra-faint galaxy, the stars do not stand still. Each one moves through the system under gravity, following an orbit within the galaxy's invisible mass distribution. These motions are small in spatial scale but large in scientific importance. The stars are few, the light is weak, and the visible body is sparse, yet the tiny differences in stellar speed provide one of the main ways astronomers infer how much mass the galaxy contains and how that mass is arranged. In such a system, motion becomes a kind of hidden language. The stars do not describe the dark matter directly, but their movements reveal the depth of the gravitational field in which they live. The key idea is simple. A star moving inside a galaxy responds to the pull of all the mass around it. If the galaxy contains only a small amount of matter, the stars do not need to move very fast to remain bound. If the galaxy contains much more mass than its light suggests, the stars can move faster while still remaining within the system. By measuring those speeds, astronomers estimate the strength of the galaxy's gravity. In ultra-faint galaxies, this is essential because the visible stars alone do not provide enough information through brightness. The system is too dim for light to serve as a reliable guide to total mass. Motion must take over where luminosity fails. These measurements usually begin with spectroscopy. Spectroscopy spreads starlight into its component wavelengths, allowing astronomers to detect tiny shifts caused by motion along the line of sight. A star moving slightly toward Earth shifts its spectral lines one way. A star moving slightly away shifts them the other way. By collecting spectra for several likely member stars in an ultra-faint galaxy, astronomers can estimate how fast those stars move relative to the system's average motion. This spread of velocities is called the velocity dispersion. A dispersion is not the same as a single orbital speed. It is the range of stellar speeds around the mean, and it provides a measure of how strongly the galaxy's gravity must hold the system together. In a large galaxy with millions or billions of visible stars, internal motion can be mapped in rich detail. One can trace rotation, changing dispersion with radius, and complex substructure. In an ultra-faint galaxy, the situation is much more delicate. There may be only a small sample of stars bright enough and confidently identified enough to measure. Each star therefore carries substantial weight in the analysis. A few stars with uncertain membership can change the inferred velocity dispersion noticeably. This means that the method is powerful, but it operates close to the edge of what the data can support. Astronomers must first decide which stars truly belong to the galaxy, and which are merely foreground stars from the Milky Way passing through the same line of sight. Once likely members are selected, the spread in their velocities begins to outline the system from within. If the stars moved only as slowly as their visible mass would predict, the galaxy would appear light in both senses, low in luminosity and low in total mass. But many ultra-faint galaxies show a velocity dispersion larger than that expectation. This is one of the most important observational clues that dark matter dominates the system. The stars move as though they inhabit a deeper gravitational well than their own starlight can create. The visible body is thin, but the internal motions imply a much more substantial invisible structure surrounding it. These motions also reveal that an ultra-faint galaxy is not simply a loose accidental grouping. A random association of stars would not usually show a coherent internal velocity pattern consistent with a bound system. A genuine galaxy, even a very small one, displays a common systemic motion together with an internal dispersion around that mean. The stars share a home and move within a common gravitational environment. This is why internal kinematics, meaning internal motion measurements, play such an important role in classification. In borderline cases, the difference between a tiny galaxy and a sparse star cluster can depend partly on whether the stellar motions imply a significant dark mass component. The interpretation, however, is not automatic. Several complications can blur the meaning of the measured speeds. One is binary motion. Some stars belong to close pairs, orbiting one another. If such a star is measured at only one or a few times, its velocity may partly reflect motion inside the binary system, rather than motion through the galaxy as a whole. In a larger galaxy with many data points, this effect may average out more easily. In an ultra-faint galaxy with only a small sample, a few unresolved binaries can inflate the inferred velocity dispersion. Astronomers therefore use repeated observations when possible, trying to separate binary variability from the broader gravitational signal of the galaxy. Another complication is equilibrium. Mass estimates from velocity dispersion usually assume that the system is approximately in dynamical equilibrium, meaning the stars are moving within a stable gravitational framework rather than in the midst of rapid disruption. If an ultra-faint galaxy is strongly affected by tides from the Milky Way, some stars may be heated or partially stripped, and their motions may no longer reflect a simple steady-state structure. In such cases, the inferred mass can become harder to interpret. The galaxy may still contain a great deal of dark matter, but the exact relation between stellar motions and total mass becomes less straightforward. Observations indicate that many ultra-faint galaxies are dark matter-dominated. Yet in individual systems it can remain uncertain how much tidal disturbance influences the measurements. Even with these challenges, the internal motions remain among the strongest tools available. They help estimate the mass enclosed within the visible stellar body. They help compare one ultra-faint galaxy with another. They help test whether the central dark matter distribution is dense or more gently varying. They also help determine whether the system behaves like a galaxy at all. In this way, a very small number of old stars become traces of a much larger unseen reality. The stars are few, but their motions carry disproportionate scientific value because almost nothing else in these galaxies can speak so directly about mass. The remarkable feature of this method is its quietness. Nothing dramatic is visible in the image of an ultra-faint galaxy. The stars simply sit in a dim, loose body against the dark, yet within that still appearance, each star is moving. Its spectrum carries a minute shift. Its speed differs slightly from its neighbours. Those tiny differences, gathered carefully and interpreted with caution, uncover the invisible depth of the system. The galaxy that seems almost empty becomes measurable from within, not by brightness, but by motion. So the inner motions of ultra-faint galaxies provide a hidden map of gravity. Their stars drift through the darkness with speeds that reveal more mass than starlight alone can explain. Velocity dispersion, membership analysis, repeated measurements, and cautious modelling allow astronomers to read this faint internal choreography. In the Milky Way halo, the smallest galaxies speak most clearly not through what they shine, but through how their ancient stars move inside the darkness that surrounds them. Ultra-faint galaxies do not begin as dim leftovers. They begin as some of the earliest small structures able to gather matter in the young universe. Their later faintness reflects not an absence of origin, but an origin on a very small scale. To understand how such galaxies form, it is necessary to step back from the present Milky Way halo and consider a much earlier setting, when the first gravitational structures are assembling out of slight density differences left from the early universe. In that setting, dark matter collapses first. It forms small halos, meaning clumps of invisible mass that gather under gravity and create the first sites where ordinary gas can collect. An ultra-faint galaxy likely begins inside one of these small dark matter halos. This sequence matters because stars do not form out of empty space. They need gas, and gas needs a gravitational shelter where it can slow, collect, cool, and become dense enough to collapse. Dark matter provides that shelter. In the young universe, small dark matter halos emerge as part of hierarchical structure formation, the process in which small structures form first and larger ones grow later through mergers and accretion. Accretion means the gradual gathering of surrounding matter under gravity. A tiny halo does not shine. It is invisible except through its gravitational effects. Yet it can still pull in ordinary matter and create the conditions in which a first small galaxy appears. The earlier stage is therefore dominated by invisible architecture. A very small halo forms from dark matter and deepens its gravitational well. Gas from the surrounding universe then falls toward that well. If the halo is massive enough, the gas can remain associated with it rather than simply passing by or staying too diffuse to matter. As the gas settles, it must lose energy in order to contract further. Cooling allows that contraction. Once the gas becomes dense enough in the inner part of the halo, stars can begin to form. In an ultra-faint galaxy, this event does not involve the building of a rich stellar city. It is a modest beginning, perhaps only a small burst or a small sequence of early star formation inside a gravitational home. Because the halo is small, every part of the process is limited. The amount of gas gathered is modest. The star-forming region is modest. The number of stars produced is modest. Nothing about the initial galaxy suggests abundance, yet that smallness is not trivial. A tiny galaxy still represents an important threshold. It means that a dark matter halo far below the scale of a major galaxy nevertheless succeeds in turning some of its ordinary matter into stars. In this way, ultra-faint galaxies show that galaxy formation reaches down to remarkably small scales. These early halos likely form at high redshift, which is the astronomical way of describing great distance in time as well as in space. A high redshift object is one seen as it was when the universe is very young. The term can sound technical, but its meaning here is simple. Ultra-faint galaxies are thought to trace very early episodes of structure growth. Their stars form near the beginning of cosmic galaxy formation, not after long periods of enrichment and repeated assembly. This helps explain why their surviving stellar populations are so ancient and why their chemical records remain so primitive. Their small halos host some of the earliest successful acts of star formation. The dark matter halo also shapes the internal character of the forming system. Because most of the mass is invisible, the visible stars are only a minor fraction of what the halo contains in total gravitational terms. Even early on, ordinary matter does not dominate the system. It falls into a pre-existing dark framework. This is why the later galaxy can contain very little starlight and still remain a true galaxy. The stars do not need to provide the main binding force. They form inside a dark matter potential well that already exists. In effect, the halo comes first as a structure, and the visible galaxy follows as a thin luminous consequence. There is strong scientific interest in exactly how small a halo can be, while still forming stars. This lower limit is important because it connects cosmology with the faintest galaxies now observed around the Milky Way. If ultra-faint galaxies inhabit extremely small halos, then they preserve information about the minimum scale on which galaxy formation works. Different theoretical models may predict different thresholds, but the broad consensus is that the smallest Milky Way dwarf galaxies form in very low-mass dark matter halos, compared with those of larger galaxies. Their present existence supports the idea that the early universe produces many small gravitational seeds, even if only a fraction become visible through star formation. Mergers and growth also belong to this early picture, though in a restrained form. A tiny halo can merge with another halo or continue accreting dark matter and gas from its surroundings. In larger galaxies, repeated mergers can transform structure on grand scales. In the ancestors of ultra-faint galaxies, growth is much more limited. Some halos may combine. Some may be absorbed into larger systems before they form many stars of their own. Others remain small and isolated long enough to form a modest stellar population that survives. The result is a population of galaxies whose roots lie in the smallest building blocks of cosmic structure. This origin in tiny halos helps explain why ultra-faint galaxies are so valuable. They are not merely shrunken versions of more familiar dwarf galaxies. They may be direct descendants of some of the first small galactic systems to light up. Their stars mark where gas once condensed inside a very small dark matter. Well, their later quietness does not erase that achievement. Instead, it preserves it in simplified form. A brighter galaxy often carries the layered memory of many phases of growth. An ultra-faint galaxy may preserve a much earlier and narrower stage. So the early formation of an ultra-faint galaxy begins with dark matter collapsing into a tiny halo in the young universe. Ordinary gas then falls into that hidden structure, cools, contracts, and forms a small ancient population of stars. The system begins small because its halo is small, but it is real in every essential sense, a gravitational home, a modest luminous body, and an early kind of galaxy. In the Milky Way halo today, these faint companions endure as evidence that even the smallest dark matter wells in the early cosmos can, under the right conditions, give rise to galaxies. Many ultra-faint galaxies appear to preserve not only an early beginning, but also an early interruption. Their stars form in the young universe, yet their later growth seems to stop quickly. This pattern has led astronomers to describe many of them as fossils of reionization. In this context, a fossil means a surviving system that preserves evidence of a major early cosmic transition. Reionization is that transition. It refers to the era when the first stars and galaxies fill the universe with energetic radiation that changes the state of the surrounding hydrogen gas. Before this change, much of the gas between galaxies is neutral, meaning its electrons remain bound to atomic nuclei. During reionization, that gas becomes ionized, with electrons separated from nuclei by incoming radiation. The universe grows more transparent to energetic light, but the smallest forming galaxies face a harsher environment. For a tiny galaxy, this change matters because ordinary gas is sensitive to heat, in a way dark matter is not. Dark matter continues to respond mainly through gravity. Gas responds through gravity and temperature together. When the cosmic radiation field intensifies during reionization, gas around very small halos becomes warmer and more difficult to capture. Gas already inside such halos can also be heated, made more extended, and less able to collapse into the dense cold clouds that star formation requires. The smallest galaxies are therefore vulnerable at exactly the stage when their visible histories are still young. Their dark matter halos remain in place, but their ability to keep gathering fresh ordinary matter can be sharply reduced. This idea helps explain the simple age structure seen in many ultra-faint galaxies. If star formation begins before or during the era of reionization, a small halo may succeed in producing an initial population of stars. But once the surrounding radiation field strengthens and the gas becomes hotter on average, the same halo may struggle to continue. It may fail to accrete new gas efficiently. It may lose part of what it already has. The remaining gas may stay too warm and too diffuse to sink back into a compact star-forming state. As a result, the galaxy does not keep building itself in the way a larger system might. It preserves an early stellar population and then enters a long, quiet age. This is why the word fossil is so fitting. The galaxy is not dead. Its stars continue to shine and orbit. Its dark matter halo continues to exist. But the main act of visible growth may belong almost entirely to the distant past. The system carries a record of what galaxy formation looks like before the universe becomes less welcoming to tiny halos. In a larger galaxy, reionization does not necessarily end star formation, because the gravitational well is deep enough to keep attracting and retaining gas. In an ultra-faint galaxy, the well is so shallow that a global change in the thermal state of the universe can have lasting consequences. Observational evidence supports this picture in a broad way. Many ultra-faint galaxies are dominated by stars older than about 12 or 13 billion years, with little sign of substantial later star formation. Their chemical evolution is limited. Their gas content is minimal. These features fit naturally with the idea that they form stars early and then experience a severe reduction in growth. Reionization is not the only possible influence on their later history, but it provides a compelling large-scale explanation for why so many small systems seem to stop evolving visibly after a brief beginning. What reionization does to small halos can be understood in simple physical terms. Gas in a shallow gravitational well is only loosely held. When that gas is cool, it can settle toward the center and help make stars. When it is heated by an external radiation field, its pressure rises, it spreads outward more easily and becomes less likely to condense. In a sufficiently small halo, this change can be decisive. The gas does not need to be expelled across great distances. It only needs to become too warm and too diffuse to remain tightly bound and to collapse efficiently. Once that happens, the galaxy's visible future becomes narrow. Its existing stars remain. Its supply of new ones fades almost to nothing. This process also helps explain why ultra-faint galaxies can be ancient without becoming chemically complex. If only a modest first generation or a few early generations of stars form before growth is cut short, then the system experiences only limited self-enrichment. The stars preserve low metal abundances and only a small chemical spread. The history is real, but it is abbreviated. Rionization does not erase what forms early. It restricts what can form later. The result is a galaxy whose visible body looks like an early chapter that is never followed by a long sequel. At the same time, astronomers use caution in applying this idea to every individual system. Rayonization is a broad and powerful framework, but local processes also matter. Early stellar feedback can remove gas. Later interaction with the Milky Way can strip gas and disturb the system. Some galaxies may preserve clearer fossil signatures than others. Observations indicate a strong connection between ultra-faint galaxies and very early star formation, yet it remains uncertain in detail how sharply reionization alone determines the fate of each one. The class as a whole fits the fossil picture well. While specific histories may vary from system to system, even with that caution, the concept is important because it links the smallest nearby galaxies to one of the major transitions in cosmic history. Rionization happens on the scale of the early universe, but its effects survive in tiny companions now orbiting the Milky Way. A faint galaxy in the halo can therefore act as a local remnant of a very distant age. Its small body, old stars, low metal content, and lack of gas all point toward an early formation followed by curtailed growth. So many ultra-faint galaxies are understood as fossils of rionization because they seem to form early, remain small, and then lose the ability to grow much further. Their dark matter halos endure, but their gas becomes too difficult to retain and cool once the young universe changes state. The stars that remain are ancient witnesses of that transition. In the Milky Way halo today, these galaxies carry a quiet but profound message. Some of the smallest galactic systems begin early, survive long, and stay faint because the young universe itself limits how much more they can become. The smallest galaxies around the Milky Way matter because they reveal what large bright systems often conceal. In a luminous galaxy, abundant stars, gas, dust, and structural complexity can obscure the simplest questions about how galaxies begin and what holds them together. In an ultra-faint galaxy, much of that complexity falls away. Very few stars remain. Little gas survives. Recent star formation is almost absent. What is left is a stripped-down galactic system in which the underlying physics becomes easier to isolate. These faint companions act less like decorative outskirts of the Milky Way and more like precise clues. They show what a galaxy can be when visible matter is reduced almost to the minimum. One of the clearest things they reveal is that galaxy formation reaches very small scales. The universe does not produce galaxies only in grand, luminous forms. It also produces tiny systems that form early, gather only a modest number of stars, and then remain quiet for most of cosmic history. This widens the meaning of the word galaxy. A galaxy is not defined by brightness or grandeur alone. It can also be a fragile, ancient, dark matter-dominated system with a visible body so faint that it barely stands out from the sky. The ultra-faint companions of the Milky Way show that the galactic category extends far downward, into a regime where only careful measurement can distinguish a real galaxy from a sparse stellar system on the edge of detection. They also reveal something important about the Milky Way itself. A giant galaxy is not fully described by its disk, bulge, and spiral arms. It also possesses an extended family of small companions whose number, distribution, and survival depend on the structure of the host halo. The ultra-faint galaxies are part of the Milky Way's long history of growth by accretion. Together they show that the halo of the Milky Way is not a simple empty surround. It is an archive of assembly, containing remnants of smaller structures from which a larger galaxy partly builds itself over time. These galaxies are equally important for the study of dark matter. Because they contain so little ordinary matter in visible form, they bring the invisible mass component into unusual prominence. Their stars act as sparse traces of a much larger gravitational framework. In this way, ultra-faint galaxies help test how dark matter behaves on the smallest galactic scales presently accessible. If dark matter forms many tiny halos, then some of those halos should host faint galaxies. If the number or internal structure of such galaxies differs from expectation, then the difference can inform the physics of dark matter itself. These systems become laboratories for asking whether the standard picture of cosmic structure remains accurate in the smallest bound galaxies. This is one reason the census of ultra-faint companions matters so much. For many years, theory appears to predict more small dark matter halos around the Milky Way than the number of dwarf satellites then observed. This tension becomes known as the missing satellites problem. The growing discovery of ultra-faint galaxies has softened that discrepancy by showing that many companions are much dimmer than earlier surveys can detect. Yet the issue is not reduced to a simple count. The faintest satellites still test whether small halos form stars efficiently, whether some remain completely dark, and how observation biases shape the apparent population. Each newly found ultra-faint galaxy therefore adds not only one more object to a catalogue, but one more constraint on how invisible structure translates into visible galaxy formation. They also illuminate the earliest epochs of cosmic history. Their old stars and low metal content indicate that many of them form close to the beginning and then preserve that early state with relatively little later alteration. In this sense, they are nearby relics of the young universe. A very distant high redshift galaxy shows early cosmic time through great distance. An ultra-faint galaxy near the Milky Way shows part of that same ancient history through survival. It brings the remote past into the local group, where individual stars can be studied one by one. This makes the galaxies powerful tools for near-field cosmology. The ultra-faint galaxies also reveal where astronomy meets uncertainty in a productive way. At the lowest end of the galactic scale, familiar distinctions become harder to maintain with complete confidence. The boundary between a true galaxy and a star cluster can narrow until classification depends on subtle evidence from chemistry, internal motion, and dark matter inference. This does not weaken the science. It strengthens it by showing where old categories must be tested against new data. A system with only dozens of visible stars can force astronomy to ask what the essential definition of a galaxy really is. The answer becomes deeper than appearance. It involves origin, gravitational structure, chemical history, and dynamical coherence. Another lesson concerns survival. The Milky Way halo is not a gentle museum case. It contains tides, motion, hot gas, and the long memory of gravitational encounters. Yet some of the faintest galaxies endure there for immense spans of time. Their survival suggests that even a tiny visible body can persist when embedded in a sufficiently protective dark matter halo, though not without cost. Their outer stars may be stripped, their gas may vanish, and their growth may stop early, but the systems themselves can remain. In this way, they show both fragility and resilience at once. Taken together, these lessons make ultra-faint galaxies far more than obscure astronomical curiosities. They are records of the Milky Way's halo, records of the early universe, and records of dark matter operating where starlight is weakest. Their small size sharpens their value, because so much has been stripped away. What remains can be unusually revealing. They show how little light a galaxy may possess and still retain a meaningful cosmic history. So the deepest significance of the ultra-faint galaxies orbiting the Milky Way lies in their ability to connect scales that usually feel far apart. In a handful of ancient stars, they connect the young universe with the present halo. In a dim stellar body, they connect visible matter with an invisible gravitational foundation. In their uncertain boundaries, they connect discovery with definition. They are the smallest companions, but they speak to the largest themes: how galaxies begin, how the Milky Way grows, how dark matter shapes structure, and how much of the cosmic past can survive in almost complete darkness. In the quiet outer darkness of the Milky Way, these tiny galaxies continue their patient passage. They do not brighten the sky in any obvious way. They do not fill the halo with crowded light. They remain slight, old, and easily overlooked, yet their smallness gives them a rare clarity. Around them, much has been stripped down to essentials. A few ancient stars endure, a thin visible body holds together, an unseen mass carries most of the weight. The long history of the young universe lingers inside systems that now appear almost absent. Their silence is part of their meaning. They are not places of strong renewal, they are places of survival. Their stars come from an early age and remain as a quiet record of what small galaxies are when growth is brief and later change is limited. They drift through the halo as remnants of early structure, preserving traces of the first stages of galaxy formation in a form that is delicate but real. The Milky Way surrounds them with a much deeper field of gravity, yet it does not erase them completely. It holds them, shapes them, and slowly tests their boundaries. Even so, some endure for immense spans of time. That endurance gives the halo a different character. It is not only the remote outskirts of a large spiral galaxy, it is also a refuge for ancient, dim companions that carry old information through darkness. In the end, the ultra-faint galaxies remain almost invisible to ordinary sight, but not to careful thought. Their weak light, their old stars, and their hidden mass bring the largest cosmic themes into one of the smallest galactic forms. They continue to orbit in silence, far from the bright disk, preserving a calm and ancient truth about how little light a galaxy can have and still remain a galaxy.